Hi, this is an example problem from Chapter 23 about RCL series circuits. Pause for a moment and read the question. Alright, so in this problem we're going to see how to solve any type of problem that deals with RCL series circuits. The picture that we see there is a really good one that explains what's going on. In Part A, we're going to calculate the impedance of the circuit. What's the impedance of the circuit? That's the overall effective resistance. So if we think about the RCL, resistor, capacitor, and inductor in the circuit, each one of those separately and independently causes some resistance to the flow of current. We want to replace those with a single value of the total resistance. We call it the impedance to current flow. We label it Z. Now, this is a series circuit. If you think about it, if we draw the current through the generator and through all of the circuit components, it's the same current that passes through all of them. So we can go ahead and replace these three elements with this single impedance. And what we find out is because this is a series replacement, we know that all the currents have the same value. So the current that goes through the generator, I'm going to write it as I peak. I'm just going to call it I peak. That's the current through the generator. It's the same current, the peak current through the resistor, the same as the peak current through the capacitor, and the same as the peak current through the inductor. Now, looking ahead, the reason why we want to calculate the impedance, because now in this picture right here, we've got a simple circuit where we can use an Ohm's-like law. So remember Ohm's law, V equals IR. Well, in this case, the voltage here is our peak voltage. We're actually going to do RMS, so let me go ahead and write this as RMS. This is the RMS value from the generator. And we can relate that to the RMS current in the circuit multiplied by the total effective resistance, the impedance Z. So to calculate the impedance, we have an equation there it shows you, or we can go look it up over here on our note sheet, a summary of RCL series circuit. Now notice that the equation for the impedance, it involves X sub L and X sub C. These are the reactances, the effective resistance of the inductor and the capacitor, and we need to calculate those. So for Part A, we're first going to calculate X sub L and X sub C. And the equation for X sub L, it's equal to 2 pi times the frequency of the oscillation of the generator multiplied by the inductance L. So to calculate this, in this we've got 60 hertz, and we have an inductance here of 0.6 Henry. And when I calculate this, I get a value 226. And you might wonder, what are the units here? Well, remember, this is a reactance is like a resistance. It impedes the flow of current, and so the units are ohms. If we actually went through and checked all the units, we know they'd be ohms. But we don't really want to do that because there's so many things going on here with units that just be sure that you're in SI units for everything. You're in hertz, you're in Henry, and then you'll end up with ohms when you calculate. Now for the capacitive reactance, the equation is 1 divided by 2 pi F times C. And so interestingly, we can see that the frequency of the AC voltage supply actually contributes to the value of the impedance. For really low frequencies, you get a big capacitive reactance, but a small inductive reactance, and vice versa. For very high frequencies, you get a large inductive reactance and a small capacitive reactance. So to calculate this, 2 pi times 60 hertz multiplied by the capacitance here, which is equal to 3.5 times 10 to the microfarads. It's minus 6 farads. Make sure I'm in the right SI unit, so when I plug everything in. I'm going to come out with ohms. And this comes out to 758 ohms. I guess I don't need to circle these yet because these are not values that they're not answers to our question yet. They're intermediate steps, right? Now that we know what the two reactances are, now we can use the equation for Z to calculate the impedance. So we're going to go ahead and take a square root of the resistance. Well, let's write the equation out real quick. So it's going to be the square root of the resistance squared plus it's the difference of XL minus XC squared. So to put all these into the equation, the resistance here is 250 ohms. Square that. Plus XL minus XC, that's 226 ohms minus 758 ohms. We're going to square that difference and then take the square root of the entire thing. That comes out to 588 ohms for the impedance. All right, now to do part B, well, now we're just looking at this simple circuit right here. And we're just going to use the simple Ohm's law right here. However, notice that we've been given the peak voltage instead of the RMS voltage. So what we're going to need to do is convert that to an RMS value. Now recall that the RMS voltage is equal to the peak voltage divided by the square root of 2. So in this case, we've got our 150 volts divided by the square root of 2, which gives us a 106 volts RMS. Now to calculate the current, we got everything we need. The RMS current is going to be equal to the RMS voltage divided by the impedance. Putting the numbers in, 106 volts divided by 588 ohms is going to end up giving us a RMS current equal to 0.18 amps. All right, now we're going to go ahead and look at part C. So for part C, we're going to want to look and remember the at the picture here. So let me go ahead and set that up. All right, so here is a picture again where we can see the series circuit RCL and its equivalent replacement just with the impedance. And since this is series again, I want to remind you that the current through all four of these things is the same. So whatever the current is through the generator, it's the same through the resistor, the capacitor, and the inductor. And of course in this picture that replaces it, it's the same current as well. So to write that, I'm going to just write RMS is same in all components. And in fact, we know what it's equal to. From part B, it's 0.18 amps. So now I want to calculate what is the voltage. So if we well, we've got the picture here, and it asks us, calculate the voltage across each of the components. So I want to know what the voltage is across resistor, the capacitor, and the inductor. Now, since we're going to be calculating the RMS value, I usually write RMS by each of these so that we remember that this is the RMS and not the peak value. To calculate this voltage, we're going to be able to use Ohm's law or an Ohm's like law for each one of these circuit elements. So let's start with the resistor. the voltage across the resistor, its RMS value. We can just use the regular old Ohm's law, VRMS equals IRMS times the resistance. Inserting the current and the resistance gives us a voltage of 45 volts across the resistor. Now for the capacitor, we can use a similar type of equation. I call it an Ohm's law-like equation. It says that the voltage across the capacitance, it's equal to I, not R, it's XC. That's the thing that resists current in a capacitor. And so in this case, remember, going to be same current again, and then we multiply by the capacitive reactance, 758 ohms. That gives us about 136 volts across the capacitor. And finally, I bet you can guess the next equation. For the inductor, an Ohm's-like law, same current, and I'm sure you guessed right, we use the inductive reactance in this case. So this is going to be 0.18 amps multiplied by 226 ohms. Let's see if we can write good over here. And that comes out to about 41 volts. Now, I want to show you something interesting. We looked at the RMS voltage before. It was 106 volts, right? Let's go ahead and see, are we able to relate that? Remember, like Kirchhoff's rule for loops would say that if we add these all up, is it going to be equal to 106 volts? No, it's not equal. That's the RMS voltage across the generator. And the reason why is because in these oscillations, the peak voltages are not reached at the same time for the resistor, capacitor, inductor, and generator. The peak voltages in each of these components are reached at different times. In other words, they're out of phase. So, you know, when one is at a high value, another one might be at 0, another one might be at a negative value. And when we add them up just using RMS values or peak values, we don't take that into account. Now, the beauty of the method we're using here is we can just completely ignore all of the out of phase oscillations, or all the oscillations in general, and we just use RMS values or peak values, and then we use Ohm's law-like equations. Now, if you actually went in and looked at the oscillations themselves, and you actually got the instantaneous values of the voltage across each of these things, then they would add up. Each component, the 3 RCL, would add to give you the same voltage as the generator. All right, we've got one more part, part D. Part D says, find the average power dissipated in the circuit. Okay. So an important thing here that we're going to learn about AC circuits is that only the resistor loses energy or consumes energy in the circuit. So the generator, that is providing energy to power the circuit, and the resistor is consuming that energy. In the capacitor and the inductor, something else happens. In the capacitor, as charge builds up on the plates, you generate an electric field, and that stores energy. And later it returns it to the circuit by contributing to the current. But there's no energy lost in the capacitor. For the inductor, similarly, when the current is changing, it generates a magnetic field, and that magnetic field stores energy in the inductor. And as that field decreases, then it gives energy back to the circuit, but no energy is lost in the inductor either. So when we calculate the average power that is consumed in the RCL circuit, if we're going to use the power equals voltage times current formula, we need to be sure that we only use the voltage across the resistor. And so we can go ahead and calculate the average power like that. We know that the voltage across the resistor, that's 45 volts. And the current, of course, 0.18 amps. That gives an average power of 8.1 watts consumed by the RCL circuit, which is just consumed by the resistor. Now, a better way to do this sometimes, so that say that you don't know what the voltage across the resistor is. Say I don't know what that is, right? Well, we can always do this. Let's use Ohm's law. Remember that the voltage across the resistor, that's equal to the current through the resistor times the resistance. And so we get this version of the power equation. And this is a nice one to use because we know that the current is the same through everything. So if we just know what the current happens to be in the RCL circuit, then we can go ahead and easily calculate the power just by taking the square of the RMS current multiplied by the resistance of the resistor. And if you check it out, you'll see that you get the exact same value, and so we know we did this correctly.